Hi, everyone. I'm Hannah. So I'm working at the University of Helsinki with the MULTIRISK project with that Marcus introduced earlier on today. And so you've heard from Samali talking about tree mortality. Now I'm going to be talking about quantifying hydraulic health of Finnish boreal forests. So I'm going to start by essentially introducing what is forest health. And then I'm going to start talking about different ways of understanding forest resilience to drought. And then what is the drought situation in Finland? And then introduce methods, talking about isohydricity and how we can scale that from trees to forests. And then comparing that with drought in Finland. And then some results. And then, yeah, at the end, maybe I have more questions than answers, but I'd like to hear from you. So what is forest health anyway? I was originally going to do some kind of introduction to forest health here, but I think most people here are more qualified to talk about it than I am. So instead, I'm going to raise a number of additional questions about forest health, because I think on the individual basis, for an individual tree, it's pretty obvious. It's either healthy, functioning, photosynthesizing, or it's infected with bark beetle. So it's pretty clear whether it's healthy, unhealthy. But then when we look at the scale of entire forests, it gets a bit more complicated how we can understand whether an ecosystem is fine, whether it's degrading, etc. So the main questions I have, maybe you can answer some, but how do we define forest health and know when it's declining? How can we attribute those declines to particular stressors or interactions between stressors? And then what are the timescales and trajectories of recovery for unhealthy forests? And finally, can we identify particularly dangerous levels of change in forest health, as in when should we actually be worried and when are we just worried about everything? So here's a forest that may or may not be healthy. So if we take away 3 trees, they're dead. Is this forest still healthy? Is this okay? If this many trees die, is this unhealthy? Is this okay? So yeah, it's kind of hard to figure out when a forest is particularly declining and how severe the threshold between a healthy forest and an unhealthy forest is. And I feel like with a lot of forest health studies, it's more like we're doing a post-mortem rather than a checkup. So often we're focused in this unhealthy region and it's kind of too late to really do anything about it. So for me, I'm more interested in this orange section here from this graph from Boreal et al. So yeah, basically what is high or low resilience and what happens in this little orange phase here. So in that orange phase, what can we do? So we can essentially try and detect early warning signs before we get to the point where all the trees are dead, it's unhealthy, it's too late. So yeah, it took me some time to try and figure out a way of thinking of forest resilience. And this is actually just borrowed from conservation science, because I think they have pretty good systems for categorizing vulnerability and etc. for species. But so forest resilience is essentially made up of the exposure, so the risk, like whether that's drought, wind, bark beetle infestations, etc. The sensitivity of that forest, so it could be somewhere that has low biodiversity, could be some particular terrain effects, or it could be the traits of the species in that system. And then adaptability, so how well is that forest equipped to recover from some kind of disturbance? Like, is it, do the species have fast growing life history, strategies, etc.? So yeah, for me, I think it's useful to think about forest health and resilience as the kind of interplay between all of these things. So focusing on what I'm actually doing, I'm interested in figuring out, are trees in Finland impacted by drought? And I guess Samali has pretty clearly shown that they are. But I also want to see, is there a threshold before all the trees are dead that we can identify some kind of declining hydraulic health? So yeah, this is the drought situation in Finland over time. So that's from 1981 to 2023. And so this is looking at SPEI, standardized precipitation evapotranspiration index. So there's a lot of different drought indices, I guess, but this one's pretty good because it also takes into account the effect of temperature. So yeah, this is kind of what's going on. There's kind of a trend that it's declining, so yes, I suppose that's happy, we can all go home. But in reality, drought is there's a lot of different characteristics to drought. You've got drought severity, drought extent, drought duration, and drought frequency. And all of these different types of drought have different impacts, I suppose, on ecosystems. And so when we go back, so yeah, this is just the drought severity in Finland. So we can see some areas where this year has had more severity than other years. But then when we look at the different types of drought, we can see that there is kind of an upward trend in extreme drought, severe drought, and moderate drought. So yeah, it kind of depends how these different types of drought impact trees. Oh, sorry. And this is also drought extent. So this isn't just the severity now. So this is the increase. So sorry, the extreme, severe, and moderate drought are increasing like the extent in Finland during this time. So now I'm going on to remote sensing. So there's a lot of different ways you can use remote sensing, obviously, to monitor forest condition. And yeah, I suppose some of the most popular methods are through image-based satellite methods. But so the issues with that are twofold. So one, obviously you have noise, or well, you have missing data where it's cloudy, etc. But then also if you're looking at greenness indices or looking at what's the word? Anyway, greenness indices, there's a bit of a time lag between what's actually happening and what you see in an image. And so if you're looking at changes in biomass, whether that's through leaf phenology or the forest is entirely gone, there is a time lag between the disturbance and what you see. So I'm using this thing called vegetation optical depth, or VOD, which is microwave signal. So the benefits are it is not sensitive to cloudy days. Doesn't matter whether it's daytime either. So it's continually collecting information, I suppose, on forest condition, whether it's day, whether it's night, whether there's clouds or not. So that's good. And it's essentially a measure of how much free water there is. So water that isn't chemically bound in a tree. So higher frequencies of VOD are more sensitive to the top level, like canopy, leaves, branches, and lower frequencies have increasing sensitivity to trunks and soils. So probably one of the most well-known uses of this is through soil moisture mapping. But so when it's split into the soil and vegetation, the vegetation optical depth generally has a linear relationship with vegetation water content. I say probably because it still needs quite a lot of testing, but there's a lot of promising studies from in situ comparisons. So some of the cons of VOD. It's a mixed signal. So basically what one pixel, the information, has is just like this cloud of water. So there's no vertical or horizontal variability in what you see. So the problem with that is you don't know whether that's a signal of how big the tree is or if it's actually stressed. So the timescale that you look at VOD is really important, because when you look at years to decades, you're most probably looking at differences in biomass and structure, which is useful for those types of studies. And then when you look at weeks to months, you're probably more likely looking at leaf phenology, drought resistance and recovery. And then if you look at daily timescales, so night and day, you can be fairly confident that what you're seeing is actually due to water stress, unless somebody went down and cut down that forest between midnight and noon. So yeah, so that's the level that I'm focusing on. So now I'm going to introduce isohydricity. So it's essentially a measure of the relative sensitivity of stomatal conductance and plant hydraulic conductance to decreasing water availability. So this is basically usually used at the experimental level. And so here it's essentially the difference between midday leaf water potential and pre-dawn leaf water potential. Yeah, and so basically plants will have, they will exist somewhere on the spectrum of isohydricity. So whether they are tending to maintain a kind of like steady midday leaf water potential with soil water potential, or if they're more anisohydric, then they tend to kind of follow the leaf water potential. The soil leaf water potential follows water soil potential. And these are essentially kind of a riskier strategy or a safer strategy, depending on the environment you're in. Yeah. So extending that to satellite data. So if we go with the concept that vegetation water content is linearly correlated with VOD, then we can take midday VOD measurements and midnight measurements and essentially kind of replace them for this like experimental isohydricity metric. So this is an example of two different pixels where one is more isohydric and one is more anisohydric. And then, sorry, the black line is precipitation. So on the left, we've got a more isohydric pixel where you can see that there's a bit of a tighter stomatal regulation there, like don't care about the water, I'm just getting carbon. That's the plan. And then in this other pixel, you can see it's more closely following the amount of precipitation. So in trait research, often it's like we like to categorize things like you're either isohydric or you're anisohydric, and that's just how you are. But in reality, plants probably do change this strategy. You know, it's a case of value. So in the boreal regions, they tend to be more isohydric because it's, well, has been more of a light limiting system. So, you know, you got loads of water, not much light. So you're just going to keep your stomata open and try and assimilate carbon. But when that changes, are you going to still just try and get carbon and lose loads of water in the meantime? Just seems a bit silly. So yeah, so what we did was take isohydricity from like VOD measurements and essentially calculate the sigma, this like level of isohydricity, and trying to see how it changes over time between years and how does that relate to drought. So yeah, this is basically what we found. So there's a correlation between SPACE6, so meteorological drought rather than hydrological drought over time. So it's just looking at the severity in each summer. And so here basically what we're seeing is you have kind of more isohydric pixels in general, but then in 2006, where it seems like there's a higher drought severity, you do see also like a change in the direction of isohydricity. So what is that saying? Does it mean that higher drought severity equals higher water stress? Like, maybe. Yeah, so, and this is basically how sigma isohydricity changed over the time period 2003 to 2011. So these pixels in red are the areas where they were becoming more anisohydric, as in, yeah, kind of there was increased coupling with drought in these areas. So yes, my question is, does it indicate really a change in water stress. And so here there's a global map of isohydricity, and you can see in the boreal regions, they tend to be more isohydric. So they're usually just like, whatever, I'll just assimilate carbon, it's fine. But yeah, so this is the combination of SPEI, but also NDVI anomalies. So this is over, the whole time period of SPEI, so kind of like 40 odd years. And so this is basically looking at regions where there was increased coupling with water limitation as opposed to light limitation. So the boreal regions tend to be, classified as humid, not water limited, but this map shows that there is increasing coupling of drought and at least vegetation productivity. So yeah. So what are my concluding remarks? So can we detect forest responses to drought? I will say tentatively yes. We do see a change in the water use strategies here, in 2006 at least. Can we define a threshold of declining hydraulic health? I'm going to say maybe. So this hasn't really been, like, I don't know whether those trees are dead. I don't know the outcome there. All you can see is really like what happened in terms of isohydricity, but it could be useful to say that this is an indication of water stress, like potentially before trees are dead. So what we do need is, I guess, what Samali's working on, data on the consequences of drought. So in those areas, do we actually see some kind of effect of the change in isohydricity over time, as well as interactions with other risk factors? So yeah, I think that's basically it. So